Hello everyone, welcome to the fifth lecture of the sixth module, which is on sequential circuit design. So far we have discussed about different ways of realizing your flip-flops, latches, registers. So one of the most, I would say, promising ways was that bistable element that we discussed, and even the SR latch that we discussed uses a similar principle, right? And all these mux-based or transmission gate-based designs, they are basically developed upon that bistable element itself. So that bistable element comes in the class of circuits which is known as multivibrator circuit. So in this lecture, we will be discussing about other forms of bistable multivibrator circuits as well as the other variants of the multivibrator circuits. The disclaimers remain the same. So there are different multivibrator circuits. So all these multivibrator circuits have different stable states, or they can have different quasi-stable states as well. So far, we have been discussing about the bistable multivibrator, where you have two stable states and the system can be in either of the two. It may have some quasi-stable state like the C point in the cascaded inverter pair, but there the problem is, given there is any noise in the system, even if you bias it at this quasi-stable point, it will gradually move to either S or like to either of the stable states. This S and R represent your SR flip-flop, where these were the stable states. I mean, not stable states actually. This is just representing two states. It has nothing to do with SR flip-flop or something. So flip-flop was something which was which we discussed in detail. In this lecture, we will be discussing about another class of bistable multivibrator circuits, which is known as Schmidt trigger. Apart from this, we have other variants of this multivibrator circuit as well. One of the variants is this mono-shot or monostable multivibrator. So in monostable multivibrator, what you have is you have one stable state and the other state is quasi-stable. And it is generally used to generate a clock pulse of predetermined pulse width. So the moment you trigger this circuit with an external input or with any transition event, what happens? The system goes from this stable state to the quasi-stable state and eventually returns back. And the time period that it takes to return back to its initial stable position, that is generally the clock pulse width, which you have generated using this monostable or like one-shot circuit. So as I discussed, it has got only one stable state, and trigger event forces circuit to the quasi-stable state. However, it eventually returns back to the original state. And after what time? The time is kind of deterministic. It depends upon the circuit configuration, the topology, and hence you can create a particular one-shot pulse of a particular width. That is its main use. That is why it's also called one shot. And you can use a simple delay element to realize this. For instance, let's say we have a circuit like this where we have two inputs of a XOR. So we have a XOR, we have two inputs. If the same input is going into it, then what is the output? Output is 0, right? So XOR, whenever the inputs are different, only then it shows you 1. Otherwise, if the inputs are same, it shows you a 0. Now, if you introduce a delay element in the path of one of the paths, then what happens? This input gets reflected only after a delay, only after the delay element at this stage. So let's say you're applying this pulse over here. So this is 1, but this 1 will reflect here only after TD time. So till that point, let's say it was 0, so it will remain 0. So when this is 1, this is 0. For TD time, what happens? The output remains 1. And then again, when this 1 is reflected over here, the output becomes 0, right? So after delay, after this TD time, this output again becomes equal, and as such, the output goes to this input again becomes 1, 1, and then this final output of the circuit goes to 0. And hence, just by introducing a delay element in this path, you have been able to generate a clock pulse, or I would say a one-shot pulse of time period TD, right? Now, the pulse is of length equal to the delay time, that's obvious. Now there is another class of this multivibrator circuit, which is also known as astable multivibrator. It hasn't got any stable state. Both of these states are quasi-stable, and as such, they are usually oscillators. And these oscillators are used to generate what? They are used to generate on-chip clocks. So most of these clocks that you have on chip, they are generated using astable multivibrators. Okay. So now first, let us discuss the bistable multivibrator, which we haven't discussed in detail till now, which is Schmidt trigger. So what exactly is Schmidt trigger? So Schmidt trigger is generally used for generating a fast transition at output when the input waveform is slow changing or when you have a very noisy input. So it is used for pulse shaping basically. So if you have a very slowly changing input waveform, where the rise and fall times are pretty high, or if you have a very noisy input which is ringing, then what you do is you pass it through Schmidt trigger and then you generate an appropriate pulse which is suitable for your circuits, right? Because if you have a very slowly changing pulse, then it would lead to large short circuit, power dissipation, also a large delay, because your delay is also it is also a function of the rise and fall times of the input, right? So Schmidt trigger is generally used for such purposes wherever you need to generate a fast transition at the output in case your input waveform is slowly changing or it's very noisy. There's a ringing in the, there's a ringing. So what's special about Schmidt trigger? So Schmidt trigger basically displays two different switching thresholds, two different VMs, depending upon what is the signal direction of the input. So this is a common VTC of your Schmidt trigger circuit. So here you can see that for when the input is going from 0 to 1, you have a different VM which we call as VM plus, and when the input is going from 1 to 0, you have a different VM which is called VM minus, right? So if you so how do you calculate this VM? So you just make this y equals to x graph over here and v out equals to v graph over here, like line over here, and wherever it intersects, you see that is giving you VM minus and VM plus. VOH and VOL are same, and how do you find out VIH and VIL? You just take wherever the slope is 1, that is determining the point at which the transition begins from low slope region to the high slope region. So you see that VIH is here and VIL is here, right? Now what can you say about the noise margins? So the best part about this is, so positive going pulse and negative going signals have different threshold voltages, fine. And what is hysteresis voltage? So hysteresis voltage is basically the difference between these two threshold voltages, VM plus minus VM minus. Why I have shown this VIH and VIL is because this will have a noise margin. I mean, here the noise margin high as well as the noise margin low can be larger than 0.5 VDD simultaneously. So that's the advantage. Typically what you have is noise margin high plus noise margin low is equals to VDD, right? But here, because of this varying thresholds, what you can get is both noise margin can be greater than 0.5 VDD. So it's a boon for us, right? Also, you can change the threshold voltage values by changing the device sizes when you're making it using CMOS. And this hysteresis, it kind of rejects any ringing on the signal. For instance, if you have input waveform which is ringing like this, so one is very noisy. And if your threshold voltage is adjusted such that VM plus is like this. So if the input is going from 0 to 1, I mean if the input is going in the positive direction, you see, at VM, what will happen? At VM, it gets 1. Right? At VM plus, it gets 1. And then it remains 1 until until the input going from 1 to 0 hits this VM minus. And since the difference between VM plus and VM minus is quite large, so you see that even when this is ringing significantly, you are getting only one output and it remains stable at 1, right? So unless this pulse going from unless this input going from 1 to 0 hits this VM minus, this won't fall to 0. It will remain at 1. So that's the advantage, right? So the hysteresis kind of rejects the ringing on the signal, and this can also be used as a regenerative circuit. Why? Because it is it can be used to produce a fast transition at the output. So it can also be used as regenerative circuit. And what exactly leads to this kind of behavior, this kind of hysteretic behavior? So here also the impact, it's the result of a positive feedback mechanism. So you may have heard in your analog circuit design in 210 course that negative feedback is very important. Positive feedback leads to unstable systems. But you just see how this positive feedback has been used so long in digital circuits to our own benefit. The Schmidt trigger circuit, or even your entire batch of sequential circuits, registers, they use positive feedback mechanism, right? So you see, positive feedback is also not bad. I mean, in terms of digital circuits, positive feedback is not at all harming. Okay. So now let us discuss one of the implementations or CMOS implementations of Schmidt trigger circuit. So this is one of the implementation of Schmidt trigger circuit. you have an inverter, and then you have these additional PMOS and NMOS. So here you have a CMOS inverter, and then input is connected to a CMOS inverter, and then we have this circuit which is providing you a positive feedback. So what do we have here? We have here a PMOSFET and an NMOSFET, and this output of an additional inverter is connected to the input of this PMOSFET as well as the input of this NMOSFET. So the second stage is basically the part which shifts the threshold voltage of this inverter, of the first inverter, VM of this inverter. Let's see what is happening. So we already discussed that the Kn by Kp ratio dictates VM. So if Kn by Kp ratio is large, that is if pull down is stronger than pull up, what happens? VM is small. That is, the circuit is able to pull down the voltage, pull down the output at a lower voltage of V. Right? That is what we saw. And if Kn by Kp ratio is less than 1, that is your pull-up network is stronger, then this network is able to pull the output up for a larger value of Vn. Right? So Vm increases in that case. So let's take two cases. So let's take the case when Vn is going from 0 to 1. Right? So when Vn is going from 0 to 1, when Vn is 0 and it's going to 1, so when Vn is 0, node X is at 1, and then Vout is also close to 0. So when Vout is close to 0, this is turned off, this is turned on, and then this node X is charged with the help of this M2 and M4 in parallel, and M1 is the only thing which is discharging. Since M2 and M4 both are kind of pulling this node up, so your pull-up network is stronger, and as such your VM will increase, right? So going from 0 to 1, you will have a larger VM for the circuit as compared to VDD by 2. Now let's take the case when Vn is 1 and it's going to 0. So when Vn is 1, this node X is at 0 and this is also at 1. Then M3 is turned on, M4 is turned off. So effectively M1 and M3 pull this node down to ground, and M2 is the only thing which is trying to pull this up to VDD. So your pull down network is stronger, and as such your VM reduces below 0.5 VDD, right? So this decreases your VM. So depending upon whether Vn is going from 0 to 1 or whether it's going from 1 to 0, you have different values of VM, the threshold voltage, right? And that kind of leads to a Schmidt trigger kind of circuit, right? Now let us discuss about an astable multivibrator circuit, which is also called ring oscillator. We already discussed about this ring oscillator, right? That it consists of odd number of inverter pairs, not pairs. It consists of odd number of inverters arranged in a circular shape. So here I've just so as to ensure that these are total number of inverter is odd, I have just mentioned it as 2n minus 1. 2n plus 1 would have also done it, but 2n minus 1 is also an odd number. So here we have 2n minus 1 inverters placed in series, cascaded in series, and then it is fed back to the first. Since you have odd number of inverters, so there won't be any stable point. Why? Because in odd number of inverters, if this is 0, the output will be 1, and then again it will be fed here. So then again this it again will be 1, and then it will be propagated, and then this will become 0. So it oscillates between 1 and 0, 1 and 0 continuously. So it's like an oscillator, and it has got no stable operating point, right? It cannot be stable at one point. And what is the delay, or what is the time period of one cycle, that is going from 0 and again to going from 0 to 1, and then again 1 from 0, going from 0 to 1 and again 1 to 0. What is the time period of that? We already discussed that it is twice of this delay of this loop, right? So it's 2n minus 1, which is the number of total inverters here, into 2 into Tp, where Tp is the time period of one inverter. And we already discussed this while discussing ring oscillators, that we have to make sure that this delay or the time period has to be much greater than the transition time, I mean the high to low or the low to high transition time. Why? Because if it is not the case, then oscillator dampens with time. I mean the oscillations dampen. You won't get perfect oscillations. Also, if you tap the voltages at these intermediate nodes, then what you will get? You will get phase shifted signals. So it would be a good exercise to find out the phase shift between at VON, to find out the phase shift at V1, VO1, VO2, VO3, and VO2n minus 1 as compared to VO1, right? So you can see that V1, V3, V5, they are phase shifted with respect to one another. And this is how you get oscillations when you are working with the ring oscillator. So this can be used to generate a clock with a particular time period, fixed clock basically, with a particular frequency, fixed clock. However, in different circuits or in different designs, you may require clock signals to also change, as per your operation. For instance, in clock gating, I mean, or here, like in your computer systems also, in your laptops, basically, you want to reduce the frequency of operation or frequency of clock when your power is a major concern, right? You want your circuit to operate at a lower frequency so that you can conserve some power. So you want to have an oscillator whose frequency is changing with voltage, or which frequency can be tuned depending upon the remaining power left or something like that, some control signal. So for that, we need to have something which is a tunable oscillator. So for tunable oscillator, one of the best ways of doing it is using a voltage controlled oscillator. So a fixed, like your ring oscillator can generate a clock with a fixed frequency. However, if you want a tunable frequency, then you have to go for this voltage controlled oscillator, where the frequency is a function of some control voltage. So what we do here is we just replace these inverters, like these simple inverters, with a current starved inverter. What is a current starved inverter? So in a current starved inverter, we just add an additional P MOSFET in the pull-up network or an additional N MOSFET in the pull-down network, and we control its operation with the help of this P control. So here I have just shown a current starved inverter in which an N MOSFET has been added in series with the pull-down network. You can also get a current starved inverter in which you add a pull-up like a P MOSFET, and that is controlled by V control. So that is also possible. So let us see what happens here. So this control voltage over here dictates the overall discharging current. So when the input is 1, then this discharging of this is actually dependent upon M1 strength as well as M3 strength. And since M3's driving strength is dependent upon its gate voltage, which is V control, so the amount of current that flows through the pull-down network is kind of controlled by V control, and hence it can modulate your TPHL. So by modulating TPHL, you can change basically the delay of this circuit, right? Similarly, if you add PMOS, then you can also tune TPLH of this circuit, right? So if you can change both TPLH and TPHL, then you can change its time period or change its delay, and hence you can change its frequency, total frequency of this oscillator. However, duty cycle is something that won't remain 50% here. Think about it, what are the implications? Also, if this V control is very small, if it's in subthreshold regime, if this V control is so small that this M3 is biased in subthreshold regime, then there would be very small operating current, and that will lead to very low fault times. I mean, if the current that it's sinking is pretty small, then the fault times would be not low, it would be actually very high. I mean, fault times would be very high, and that is dangerous. That is somewhat dangerous. So you see that TPHL actually increases significantly as V control reduces, because if it goes into that subthreshold mode of conduction, then the current is pretty small, and as such TPHL increases significantly. So what you can do in that case is, if you have a very high fault time, and it's large fault time basically, not a low fault time. If it's a low fault time, it's actually good for us. If it's a large fault time due to the low operating current, then it's a problem for us. And then what you do is, instead of having this feeding another such gate, you feed it to a CMOS inverter or Schmitt trigger for regeneration, right? So another point is, if somehow this control voltage forces it to subthreshold regime of operation, the current goes as exponential of the VGS minus VT, right? So if there is any variation in this V control because of supply voltage variation or something, there would be huge variation in the current, exponential variation in the current, and as such, what would happen? The sensitivity of this circuit to current variation to the voltage variation in V control is large in that case. And also, if there is a noise, its impact in the subthreshold regime is also large, because the current goes as exponential of the voltage. So any noise on this terminal will lead to exponential variations in this. The general rule that foundry people or circuit designers basically employ is, whenever you are working in subthreshold regime, the impact of variation in the normal mode of operation, like in the saturation mode, if it is leading to X times change in your output, then if you are working in subthreshold regime, it will lead to at least 10x time change in the output. So when you are dealing with subthreshold, like when you are biasing your circuits in subthreshold or when you are designing subthreshold circuits, it's really important to ensure that mismatches are not significant. Because if that is the case, then what would happen? It will lead to 10x change as compared to when you are biasing it in your saturation regime. So although in subthreshold you are consuming less bias current, or I would say you're consuming, or you're kind of reducing or gaining a lot in power dissipation, but in this, at the same time you're also losing robustness to noise, you're also losing some of the speed. Okay.